Finally, for this morning, Matthew Ho.
Hello, everyone. My name is Matthew Ho, and I'm a graduating PhD student at the McWilliams Center for Cosmology. Today, I'm going to be just briefly presenting the highlights of my poster on galaxy cluster mass estimation using deep learning. So throughout this project, the main thing we're after is the masses of galaxy clusters. While masses are important for studying cosmology with large-scale structure, they are fairly elusive due to the limited information we can recover from indirect observables. One such established method of measuring cluster masses is via the fundamental first principles m sigma, which relates the overall velocity dispersion of galaxies in a cluster to the overall system mass. While fundamentally straightforward, the m sigma unfortunately doesn't generalize to real data well, since there are a number of systematics like cluster substructure, cluster mergers, and interloping galaxies, which are highly nonlinear and add considerable scatter to the relationship. The fortunate news is that we have been able to identify these systematics relatively early on because they appear as artifacts in distributions of observables like the dynamical phase space, such as this example of dynamical substructure shown here. So we figured if the artifacts producing this error are recognizable by eye, then this would be an ideal situation in which image recognition tools like CNNs could improve our measurements. So we built a model which takes distributions of these observables as input, turns them into images via some kernel density estimation mapping, and relates them to an overall mass estimate in a complex nonlinear manner. So in our paper published in 2019, we found that such a model was able to identify features representative of these systematics, like cluster substructure and interlopers, and mitigate their effects on a dynamical mass prediction. The highlights of this work were that using deep learning, we were able to beat traditional m sigma measurement scatter by a factor of 2.5 and beat idealized m sigma measurements by a factor of 30%. So following this, we decided that to do cosmology, we needed not just a way of measuring these masses, but also methods for reconstructing our predictive uncertainty. So in a follow-up paper published early this year, we extended this model using approximate Bayesian techniques to predict both mass and uncertainty for each cluster in our test set. So in doing so, we were able to marginalize our over uncertainty in our model parameters using the traditional dropout marginalization techniques presented in the literature. We found that we were able to recover mass posteriors extremely well with high consistency with true cluster mass. Among this, the most notable consistent was that for mid-mass clusters, our models could recover 64th and 90% confidence intervals to within 1% of their empirical value. So lastly, now that our theory had kind of been established, the next step towards eventually applying these models on next generation survey data would be to verify these predictions on well-studied systems. In a letter currently in review at Nature Astronomy, we've applied these models to observational data from the famous Coma cluster. And we study how these mass predictions vary according to various choices of training simulations. And overall, we show strong historical consistency with other probes of Coma's mass. In addition, we have recently extended this model to do predictions on other well-studied systems, like the clash clusters, using more realistic photometrically selected training data. So be on the lookout for these two papers on Coma and the clash clusters on arXiv sometime in the next month. Lastly, I'd like to say thank you to the organizers for having me, and I'd be happy to take any questions in the Slack.
Thank you. And let's have a big hand for all the presenters of this morning.